Hi everyone, I'm Emily and I'm going to be presenting over the analysis of serotonin present in crayfish hemolymph using derivatization by MSTFA and BSCFA through GCMS. So why are we interested in serotonin? Serotonin is involved with mood, specifically aggression. It is hypothesized that higher levels of serotonin are going to correlate with lower levels of aggression, and lower levels of serotonin are going to correlate with higher levels of aggression. So if one were to have a higher level of serotonin, thus a lower aggression level, you might be calmed and relaxed. Whereas if you had a lower serotonin level, thus a higher aggression you might be fighting or hiding or in that fight or flight response. So we're interested in serotonin, but why are we interested in serotonin in crayfish? So crayfish are actually one of the only other living organisms that naturally produce serotonin, much like humans do. So their serotonin is going to be found in their hemolymph. Hemolymph is just the equivalent of blood is to humans. And then we are going to be able to observe their behaviors and aggression visibly, and then be able to quantify our levels of serotonin to those aggression behaviors. So serotonin in crayfish hemolymph is going to be in minute amounts. So we have decided to use the GCMS or the gas chromatography coupled with mass spectrometry. The reason we chose the GC is because it's going to have a low limit of detection, so it will be able to quantify those minute amounts of serotonin in the hemolymph. The GC also will be able to separate the serotonin from all the other stuff within the hemolymph so that we can be able to easily separate the serotonin and each of its derivatives. And then finally, the MS will be able to help us identify what each peak is by giving us a mass spec, and each of those will be unique to each analyte that comes out, and we will talk about how both of these work together in more detail in a later slide. So before we can actually inject serotonin into the GC, we have to first derivatize it. So serotonin is a polar molecule, and here you can see 4 active hydrogens on that serotonin structure. So those hydrogens will have to become nonpolar silane groups, and we will do this with using derivatizing agents such as MSTFA and BSCFA. So MSTFA is going to be N-methyl and trimethylsilyl trifluoroacetamide, and BSCFA will be NO bis-trimethylsilyl trifluoroacetamide. So the difference between the two is MSTFA is going to be a more universal derivatizing agent and better at derivatizing more things, whereas BSTFA is going to be better at derivatizing those amine groups, which serotonin has 3 of its 4 active hydrogens on an amine group. So we have opted to use BSTFA over MSTFA in this case. So we've briefly touched on how kind of everything works, but here's how it really works. So we will start off with in a gas. Ours is going to be helium. It is an inert gas, so it's not going to react with anything. It's just going to kind of help us push our analyte through our GC column and out to the detector. So our sample will be injected into the injector port there. Our injector port is usually heated. Ours is going to be heated to about 230 degrees Celsius. And then it will flow through into a column, which is usually a nonpolar column in a heated oven. And then it will flow out to a detector. Our detector is going to be a mass spectrometer, and our MS is going to ionize and fragment the analyte that comes through. So the fragments can then be pieced back together based on their mass to charge ratio, and that will come out as a mass spectra, and that each mass spectra is going to be unique to each molecule and each derivative. So here we can see some of serotonin and its derivatives here. So on the far left we have serotonin in its pure form, and then just below that we have its first derivative. That first derivative is going to be on that oxygen because that hydrogen there is going to be the most polar, most reactive, so it is going to be able to fall off easily and be replaced with that silane group there. And then we have 2 different 2-TMS derivatives. So we have a little bit of coding there. So Rn is going to stand for ring nitrogen, whereas N is just going to stand for that N nitrogen there. So we will start with that first TMS on the oxygen, and then either end will form that second TMS. So here we also have two different types of 3-TMS, again with the RN and N coding there. So those are going to be differentiated within the mass spectra that we talked about on the previous slide, and as well with the two different 2-TMS derivatives. So each of those is going to fragment in slightly different ways, so they will again produce different mass spectra compared to the other. And then finally on the end there we have our 4-TMS derivative. So like I previously stated, we have to derivatize serotonin prior to injecting it into the GC column. So we do this by dissolving our pure serotonin into highly pure methanol for a stock solution. And then of that stock solution, we are pipetting 1 milliliter of it into our rinsed vials. Our rinsed vials are rinsed with that highly pure methanol to get rid of any impurities or anything else that could react within our reaction. And then once that is in our vials, we evaporate the methanol once again so that we are left with only serotonin in those nanogram amounts. And then once all the methanol is evaporated, we add our highly pure pyridine, which is going to be our catalyst, and then our derivatizing agent, our BSTFA. So with pyridine being our catalyst, that is going in with serotonin to create a blank since it is not reacting with anything. And then once those are all made, we incubate in an oven, and then we finally will run it through the GCMS. So once all of our samples are made, we have set some parameters. So as you can see here, our column is going to be a nonpolar column, like I previously mentioned on our GC slide. Our inert gas, our helium, is going to be flowing at a rate of 1.2 milliliters per minute, and our auto liquid sampler will be injecting 1 microliter of our sample into the GC at a 2-to-1 split ratio. So the split ratio is to help decrease the intensity and yield more accurate results so that our peaks do not plateau at the top. So that means 2 parts will go into waste and 1 part will go through the column. We will start our GC at 60 degrees Celsius for 1 minute, start a ramp at 10 degrees Celsius per minute to 325 degrees Celsius, and then we will sit there at a 10-minute hold at the end. And then finally, our MS scan rate will be 9.1 scans per second, and it will be ranging from the 45 to 600 atomic mass unit range. So here we have our chromatograms and what we will be looking for. So our serotonin peak is going to come out at about 18 minutes, our 1-TMS derivative at about 18.2, 18.3 minutes, our first 2-TMS derivative, which is going to be the oxygen and ring nitrogen version, at about 18.8 minutes, our second 2-TMS derivative at about 19.5 minutes, our first 3-TMS derivative, which is going to be at the 3 different binding sites at about 19.6, and then finally at the right we have our 4-TMS derivative at about 21.7 minutes, and then our 3-TMS derivative at 21.8 minutes. So once we have found out where our serotonin is going to come out in the chromatograms, we have started doing a variety of different tests. So our first test is going to be varying our incubation time in the oven prior to injection. So we incubated at 80 degrees Celsius, and then all of our vials had the same amount of BSTFA and pyridine in them, except they were just incubating at different times. So as you can see, as time went on, our 1-TMS derivative decreased to almost nothing, and our 4-TMS continued to increase. Our 3-TMS had a slight increase in the beginning, but then it started to decrease again as 4-TMS started to make its way. So in this test, we varied our BSTFA amounts. So each vial was incubated for 2 hours at 80 degrees Celsius, and we kept a total of 700 microliters in each vial. So here we can see that the 10 microliters of BSTFA only yielded the 1-TMS derivative. However, when we increased our BSTFA amount, the 4-TMS started to show up more and more. We also decided to run a replicate of 150 microliters of BSTFA and 300 microliters of BSTFA to see if it was still reacting while it was waiting on our auto liquid sampler. As you can see, trial 2, which ran after trial 1, did produce more 4-TMS in comparison to the first trial. We also noticed that as we got to higher and higher amounts of BSTFA, we kind of started to plateau in our 4-TMS production. We will see that same trend on the next slide, so I'll go into our hypothesis about why this may be occurring on the next slide. So in this test, we have decided to look at the time outside of the oven. We incubated our samples at 80 degrees for 8.5 hours. Again, we kept that same 700 microliter total. And again, like I mentioned from the previous slide, we see the same trend between the 150 and 300 microliters of BSTFA. However, when you look at trial 1 and trial 2, you can tell that trial 2, which ran later in our sample, has produced more 4-TMS compared to the first trial. So some hypotheses that we have come up with as to why 300 is producing less 4-TMS is maybe because the end nitrogen is hindered, so to become more stable, one of those silane groups is falling off again and reacting either with the excess BSTFA or even other things as well, but we still need to do a little bit more research on that. So our final test was a reproducibility test. So this is where we took one vial and then we just took multiple samples from that singular vial. That vial was placed in the incubation oven for 2 hours at 80 degrees Celsius and then placed on our auto liquid sampler. As you can see in our first run, we still have quite a bit of 2-TMS left and not as much 4 or 3-TMS in comparison to later on down in our subsequent runs. So once we get to the 6th run, we have the most 4-TMS compared to all the other runs and the least amount of 2-TMS. So we can see that as time goes on, the reaction is still occurring. So to kind of sum up our findings from our results, we have found that BSTFA is definitely better at derivatizing those amine groups there, as well as higher temperatures in our incubation and longer incubation times have kind of pushed that reaction towards a 4-TMS derivative. And then we have also found that more 4-TMS derivative is forming as the vials sit out, and so thus longer time outside of the oven is producing more 4-TMS as well. So we still have a couple questions unanswered, so within our next steps we are going to try an ice bath method. So that is just doing another reproducibility test, but instead placing the vials in an ice bath after incubation to kind of help stop that reaction from proceeding as it's sitting in the auto liquid sampler. And then we will also be starting with using hemolymph from the crayfish, and we will have to be able to separate the proteins from the hemolymph and then derivatize the serotonin and all the other stuff that will also be in the hemolymph and how to kind of go around that as well. We will also be looking at dopamine standards because, as you can see here, the structures are going to be similar. So we have serotonin on the left and dopamine on the right. The structures are going to be similar and they're both going to be present in the hemolymph and even in humans as well. So it'll just be interesting to see what that produces as well. And finally, I just want to thank Dr. Milky, who has been my mentor, Madison Wagner, and Dr. Moore, both from Bowling Green, for providing me with this opportunity to help them in this project. And then finally, I just want to thank all of you for tuning in, and I look forward to answering any of your questions. Thanks.